Hello, class. This is Miss Smith here. I am having technical difficulties putting up the video that I loaded, so I'm taking this one on my cell phone. So I apologize if it's shaky and low quality, but I needed to get it put up so you would have your notes for tomorrow. So this video is going to be discussing sound waves. And we are going to talk about what is sound, how do sound waves travel, how do physical properties of a medium affect the speed of sound, what properties of waves affect what we hear, and we will talk a little bit about the Doppler effect. So, sound is just vibrations that travel through the air or another medium. And remember, medium is any matter that sound waves travel through. When these vibrations reach the air near your ears, you hear the sound. So let's think about this for a minute. If a tree falls in a forest and no one is there to hear it, does the falling tree make a sound? Well, let's think about it. Do you think that you have to be able to hear vibrations for there to be sound? Do you think that energy is produced by vibrations even if no one is there to hear it? Well, the answer is, of course. If a tree falls in the forest and no one's there to hear it, it still makes a sound. And throughout this video, anytime you see my friend the Incredible Hulk here, he's going to show you one of your Easter eggs. So your first Easter egg is the answer to that riddle, and that is yes. So sound waves carry energy through a medium, and that can be a solid, a liquid, or a gas, without the particles of the medium traveling along. So sound waves do not carry matter, they only carry energy. And sound waves travel as longitudinal waves. Longitudinal waves are generated when a source of energy forces the matter in a medium to vibrate. That back and forth motion pushes air particles close together, generating a compression, or moves the particles apart, generating a rarefaction. Sound waves are mechanical waves, and like any other kind of mechanical wave, they have to have a medium to travel through. So sound waves can travel through gas, air being the most common. Sound waves can travel through liquids, like we saw when we put the tuning fork into the cup of water in class, and they can travel through a solid, like we heard when we held those tuning forks to the desk and put our ear down. In outer space, however, there are no molecules to be compressed or rarefied. With no molecules, no medium, no sound can travel through outer space. So every science fiction movie you ever saw where there was a space battle and ships blew up in huge loud explosions, yeah, those were all lies. So the speed of sound depends on the physical properties of the medium it travels through. And the three physical properties that you look at are the elasticity of the medium, the density of the medium, and the temperature of the medium. So at room temperature, sound travels through air at about 342 meters per second. Elasticity is the ability of a material to bounce back after being disturbed. And remember that waves are a disturbance in matter. So solid materials tend to be more elastic than liquids or gases. You can beat on a solid and it's going to bounce right back and be exactly the same shape that it was, almost instantly. If you disturb gases or liquids, it takes them a little bit longer to settle back down into their original state. Particles of a solid don't move that far. That's why they can bounce back and forth so quickly when vibrations move through them. And this is part of what allows waves to move faster through solids. Another aspect of the medium, another physical property of the medium that needs to be considered is how much matter there is in a given amount of space, how dense it is. The more dense the medium, the faster sound can move through it. And again, that makes sense. The closer together the particles are, the faster the sound wave can get from one particle to the other. And the final physical property that you have to look at is the temperature of the medium. So, temperature, remember, is the degree or intensity of heat present in a substance or object. So in any given medium, solid, liquid, or gas, sound will travel more slowly at lower temperatures. So the colder something is, the slower it travels. And that makes sense if we remember the fact that heat is a measure of thermal energy. So very cold molecules have less energy. They don't want to move as much. So sound travels more slowly through them. They're kind of sluggish. Whereas warmer molecules have more energy already, so it's easier for the sound waves to push through and they can get through faster. So 4 properties of sound that we are going to look at are intensity, loudness, frequency, and pitch. So intensity is the amount of energy that the wave carries per second through a unit of area. And we can see how much energy a particular wave has by looking at its amplitude. And remember that the amplitude is the distance from that middle resting position to the highest point of the wave. So as amplitude increases, energy increases. And we measure this amplitude, this energy, in watts per square meter. So the loudness is what we actually hear. It's not quite the same thing as intensity, but it's related to it. So again, loudness depends on the amplitude of the sound wave. The greater the amplitude, the louder the sound. And we measure loudness in decibels. And if we look over here at this decibel chart, we can see how many decibels different things are. And a whisper is about 20 decibels. A quiet room is about 30. There we and the highest safe volume is about 85 decibels, which if you look is somewhere between a really loud radio and a bass drum. If you get into decibels higher than that for any extended length of time, like if you blast your headphones for too long, you can actually cause permanent hearing damage. So you want to keep your noise pollution down. You want to keep it under that 85 decibel threshold. So another property of sound waves is frequency. And frequency is the number of vibrations that occur per second. Wavelength changes with frequency. When you have a larger wavelength, you have a lower frequency. Short wavelengths give us high frequency waves. Frequency is measured in hertz. So if a wave is 50 hertz, that means it has about 50 vibrations per second. And remember that frequency controls the pitch of the sound, whether we hear it as a high-pitched or a low-pitched sound. So, some examples might be a dog whistle that makes a very, very high-pitched sound. In fact, a lot of dog whistles make sound that is so high-pitched that human ears can't even hear it. Only dog ears can. While a tuba would make a very, very low-pitched sound. And there's the Incredible Hulk making sure we get our Easter eggs. So remember those two examples. The last thing that we are going to talk about is the Doppler effect. And the textbook definition of the Doppler effect is the apparent change in frequency as a wave source moves in relation to the listener. And put simply, this just means that sounds moving toward a person push the waves together and cause them to move at a higher frequency. So the pitch appears to the listener to increase or get higher. Whereas if something that is making sound is moving away from the listener, the waves spread out and we hear them at a lower frequency and the pitch appears to decrease. And a really good example of that would be an ambulance moving either towards an observer or away from an observer. All right, everybody. I once again apologize for the poor quality and the cell phone video, but I'm doing the best I can, and I will see you in class tomorrow. Bye, guys.